Hello, hello. Oops, oopsie. Wait, hold on. Adjust this thing here. And then, where are we? All right, all right. 1, 2, 3. Good afternoon. Oh, God, it's Friday afternoon, right? Oh, I am very ready for the weekend. How is everyone doing, folks? Good to see you. This is Jose Luis. This is Parametric Camp, computational design live streams and tutorials and exercises and fun and all the cool things that we can do these days because we have technology, we have internet, we are connected with each other remotely, and yeah, there's a global pandemic, but honestly, we need to make some good things out of this, and one of them for me, for example, was that I started this project triggered by being locked in my apartment with COVID, and now we're like 58 live streams in, and with a bunch of playlists and interesting. I think it's interesting content. I think maybe it's helpful for people. Hopefully, I think that's why I do it personally, and I hope the community can appreciate that. I think they do. I actually get a lot of really nice words, and people reach out in a very grateful way. I'm actually very thankful for people who do that and who reach out to say that they like what we do and that it's helping them and that it's making them learn and that it's giving them opportunities. So I'm actually very thankful for that. I feel blessed that I have the opportunity to do that and that my job and my life allow me time to do this as well. So, thank you, everyone. Parametric campers, you're awesome. Thanks a lot. And you're always welcome to reach out. Okay, so let me say the spiel again. My name is Jose Luis. I run this thing called Parametric Camp. We do computational design live streams every Fridays. And we have a Discord server where we have offline conversations throughout the week. And then we also have a lot of social media that you can use to follow us and to know when we go live, etc., etc. I use particularly a lot of Instagram. So if you're an Instagram person, feel free to join us there. And I use a little bit of Twitter as well. And we also have a Google Calendar, which I'm posting links to all of that here on the chat. We have a Google Calendar where I post the events when they go live. So if you subscribe to that, you will see live stream popping up on your Google Calendar. We are this week in the middle of wrapping up a series that I'm calling Introduction to Parametric Modeling, which at this point, I'm not sure if it's an introduction anymore, but it's kind of let's call it a comprehensive introduction because I'm talking about a lot of things and I'm going into detail into a bunch of them actually. So yeah, that's kind of cool. And oh, I have some coffee on the stove. Give me 1 second. I'll be right back. I need to go get the coffee. I'll be right back. And I'm back. You thought you were gonna get rid of me, huh? Okie dokie. I just got my coffee. Have I ever shown you my mug? Huh? Oh. Wait, it's really hot. I'm gonna burn my face. What you see? You see the steam? Can you see the steam? Yes. Anyway, I will show you in a second. So what are we doing this afternoon? we're doing hands-on exercises. That's what we're doing. And this morning was more about transformations and like foundational exercise. This afternoon is going to be much cooler. So we're going to do an exercise that is going to be a surface. We're going to design a facade that is going to have openings optimized for sun incidence. So we're going to calculate, we're going to have a free-form surface, and then we're going to put there like circles, for example, and then we're going to have those openings, the openings of the circles, bigger or smaller depending on how strongly the sun is hitting that surface. Okay, so that's going to be one thing. We're also going to do an array of solar panels on top of some kind of dolly or servo or whatever, and they're going to be rotating, and they're going to be rotating to the sun, okay, to a sun that is going to be moving in 3D space. Then, then what else? We are going to take a building or some kind of form, we're going to chop it in sections, and then we are going to, should we do that exercise later on when we talk about, actually, you know what? I'm going to leave that exercise. We're not going to do that now. We're going to leave that to whenever we see the intersections plus Boolean operations lecture. Whenever we do make that video. So we're not going to do that now either. And what else are we going to do? We're going to make a surface, and we're going to pop out these openings that are going to look like tentacles kind of thing, and suction cups, and then we might do a brick wall. We might do a brick wall. Are we going to do a brick wall? We're going to do a brick wall. Hey, no, how are you doing, sir? Good to see you. And we're going to do a brick wall. Can we do a brick wall? We're going to do a brick wall because it's going to be cool. Yes. Brick walls rock. Okay, we're going to do a brick wall. Fine, we'll do a brick wall. I'm not sure if we're going to have time for that one, but yeah, we can try. Okay. And then Umbraco, and then we're going to do a short video to point to the yes, we can probably do that. All right, cool. So let's get started then. So let's fire up some Rhino. Let's fire up some Rhino. Yeah, we need to change that. Okay, so where was I? Oh, we were here this morning. I'm going to save this. I'm going to save this. I'm going to create a new one. And a solar facade. Okay. So how are we going to do this? Well, I should probably do a few sketches, and now I feel really conscious because Nono is here and he's going to see me drawing really bad sketches on my computer. So Nono, I ask for your forgiveness in anticipation because you're not going to like what you're going to see. right now. Okay. All right. So what is the exercise that we're going to do today? What is it going to be about? We are going to, first of all, we're going to do a facade that is optimized for some kind of solar condition. So for example, we are going to create, what are we going to do? Let's imagine that we have some kind of facade, and the facade has some kind of free form, for example. Okay? Let's imagine that this is a facade for some reason. Okay? And then what we want to do is we want to see if, how can I do colors here? How can I choose colors? Image, window, color puck. Okay. So for example, let's say that let's say that we have the sun somewhere here, and then the sun is hitting the surface. Okay. So what we want to do, oops, no, the sun should go on a different layer. We have the sun, and then the sun is hitting the surface in, for example, like this, and then like this, and no, don't look at what I'm doing right now, okay? And then it's hitting the sun like this. And then what we want to do is we want to create some kind of rule where we're going to create openings on this surface, but the openings are going to be bigger, are going to be smaller, where the sun is hitting more frontally. Okay, but then they're going to become smaller again. Oh God, why can I not even draw simple circles? Okay, and then they're going to become smaller again, and they're going to become smaller again, based on the angle of the sun. And actually, maybe what I need to do is this layer is going to go off, and then I need to create another layer, and this layer is going to be like this, like this. Oh God, this is bad. Okay. And then we're going to explain that the way we're going to do this is that we're going to have a surface. For example, we're going to have this surface. This is going to be the wall, right? And then if the sun is here, so for example, if the sun is here, actually let me move this to the right, because why? Oops. Because if the sun is here now, if the sun is here, now, if, for example, we calculate points here, we can see how, if I do some light calculations, you can see that one, and you can see that one, And we can see that this is the angle here. Now let's do omega. This is one angle, and then the other one can be this angle here. And then the sun is going to be, again, it's going to be somewhere here. And then the angle, this angle is going to be this one. So that's going to be omega here. This is going to be omega 1. This is going to be omega 2. Nah, screw those numbers. And then the next one is going to be here, and it's going to be right here, and then this one is going to be, and then this angle is going to be tiny. Which means that probably the aperture here should be rather large. Here should be smaller, and here it should be really small. How is that for a sketch? It's not absolutely terrible, right? It's just bad. But it's not the worst I've seen, and I'm going to hide this right behind my back. Yes, exactly. Oh, can I see that? No, you can't see that. Okay, so all right, so that means that the way I'm going to tell the story is going to be something like this. Where are the circles here? Actually, should I? Okay. All right. Okay, okay. So I think I'm ready to start. Are we ready to do this? Okay, solar facade. Here we go. All right. All right. Okie dokie. Okay. It's a mental centering. So we are going to do the next exercise. Going to be a solar a facade that is optimized for solar incidence. I will record the introduction at the end, and then we just start by talking about what are we doing and explaining a little bit of the process. Okay. All right, let's get started. This exercise is going to be a lot of fun, like a lot of fun. So how are we going to start? As usual, let's think through the problem a little bit. So I want to start off from some kind of free-form facade. So imagine I'm designing like a really fluid building of sorts. And what I want to do is I want to design openings in that facade that are optimized based on some kind of logic that has to do with the solar incidence. And for this exercise, we're going to imagine that, for example, this facade is in a very warm climate. It's in a very warm client, right? It's in a very warm climate. And what that means typically is that direct sun incidence on a facade in a warm climate is not a great thing because a lot of heat penetrates into the building, and typically in those climates what you're trying to do is avoid direct heat into the building. You want to keep the building cool most of the time inside. So what we can do is we want to write a rule where, depending on, so let's imagine, let's start over again. Starting over again. Let's start over again. All right, here we go. Let's get started. This exercise is going to be a lot of fun. You're going to see. I like this exercise a lot. So what are we going to do? So we're going to imagine that we're starting with some kind of free-form facade. I'm designing like a really fluid building of sorts. And then what I want to do is I want to optimize some openings in the facade of this building. And how is that going to work? Well, we're going to imagine that this building is going to be situated in some kind of very warm climate. And what happens in warm climates is that typically one of the things that you want to avoid is that you don't want to have a lot of direct sun incidence on your facade or going through your openings into the building, because that brings in a lot of heat inside of the building, and what you typically want to do is to keep the building as cool as possible inside. This is the condition for warm climates. For cold climates, it's a really different story. So the logic here would be, I want to design some openings that are optimized for the sun incidence, okay? And optimization in this case will be very related to the fact that I will want to have some of the openings be bigger wherever there is less direct sun coming in from the facade, so that I still get light, but I don't get direct sun and I don't get heat inside of the building. And then the opposite will also be true. In those areas of the facade where I have a lot of direct sun incidence, those will have the smaller openings. And how can I do that? So that's actually going to be fairly easy given the tools that we already have in our tool set. So what we're going to do is we're going to do some kind of analysis where we're going to imagine that we have the surface. This is going to be like a section of the surface. We're going to imagine that we have a sun, and for this analysis we're going to imagine that the sun is always on the same place, which is not the case. The sun is rotating over an arch and it changes inclination over the year. So the real problem is actually much more complex than we're going to do here. But we're going to imagine that we have a static sun that is always on the same position. And what we're going to do is we're going to subdivide the surface that we have into the center points of where we plan to put these openings. And then we're going to do a very simple process where we're going to cast virtual rays from this virtual sun into each one of the points. And then we're going to calculate the angle between the ray of the sun into that particular point, and then the normal, the perpendicular vector from that surface to that surface from that point. And it turns out that if that angle is very wide, then the solar incidence of the facade will be very small. And then that opening will be able to be rather large. But as soon as the inclination of the surface starts pointing towards the sun, or in other forms, as soon as the angle between the sun and the normal to the surface at that point gets smaller, then the stronger the sun is hitting that opening. And therefore, the distributions of the openings will be proportional to how little the angle is. So the larger the angle, the larger the opening, and the smaller the angle, the smaller the opening as well. And somebody is mowing the lawn. My neighbor is mowing the lawn right now. Can you hear the background noise? Can you guys hear the background noise of like somebody with a chainsaw or mowing the lawn? Oh well. So in a nutshell, that is the process that we're going to follow. We're going to subdivide the surface into a bunch of points in the UV direction. We're going to calculate the normals to the surface at each one of those points, and then we're going to calculate the angle between the sun and each one of those vectors. And then, given that value of the angle, we will design openings on that facade that will be proportional to that angle. Let's take a look at how to do that in a simple way. Well, that's great that you're not hearing because it's really loud. I guess I have a filter, I have a noise reduction filter going on, so I guess that's pretty nice because it's working really well. All right. So where am I? Where's my mouse? Here. And here, I'm out of coffee now. Nah. Mm-hmm. Okay. Oh, so you can't. Sorry, so you can't see me. All right. Okay. So here we are. Okay. So we have this facade, and then we're going to have the sun, and the sun is going to be a point. Okay. All right. So let's save this. Let's put some bifocals here. And then let's save this as and then we're going to save this too as E11 solar facade. Okay. So let's get started. So we're going to imagine that I have some surface that I have in Rhino, that I have designed, whatever, or this may actually be a surface that comes from some kind of parametric process that you have done in Grasshopper. It doesn't really make a difference. So if you had a component with a surface, you would plug that component all the way into the beginning of this definition. Otherwise, what you can do is you can just click surface, then right click, and then set this surface as the input parameter that we're going to start working with. So no matter if it comes from Rhino or Grasshopper, it doesn't matter. We have the surface as data, and then we can start working with it. So the first thing that I'm going to do is I am going to divide this surface into a grid of UV points. So I could do that with the divide surface, which if you remember, it gives me the points and the normals and the UV, and because I want the normals, this is kind of good. But you know how I like working with planes better? And we will actually need those planes at some point farther down the road. So I'm just going to opt for surface frames instead. And then what I would like to do is I would like to subdivide this into a grid of UV planes. And that's going to be, for example, I'm going to say that this is going to be 10 and 10. And actually, no, I'm going to do a little bit more than that, 15 and 15 in each direction. So U and V, and then this is going to, maybe something like that, or maybe a little more, maybe a little more dense. We can probably go a little more dense. Okay, so something like that. So these are going to be where the openings of my facade are going to be. Okay, so those are going to be the centers. And then, as we said, we are going to need to find the normal vectors on each one of the centers of my facade to the surface. So because I did frames, frames contain all the possible information. They contain the orientation, the center, but they also contain the normal. And because they are planes, so something that we can do is we can, if we want to actually extract the normal vector to start working with it at some point, what we can do is we can go to plane, to vectors, we can go to planes, and then here, just like we could construct and deconstruct points and vectors, we can also construct and deconstruct planes. So if we use the deconstruct plane component, you can see that this component takes a plane, and then what gives me in result is the origin point, the x-axis vector, the y-axis vector, and the z-axis vector, which is the normal. Just to make sure that this is what I want, I'm going to turn off this visualization. I'm also going to turn off these points. And what I'm going to do is I'm going to visualize those vectors with a vector display component. We've used this in the past, and this vector takes the vector, I want to visualize V, but it also takes anchor points. So the anchor points, I'm going to take the center of the plane, which is also given to me here in the, and you can see that indeed I am getting arrows that are sticking out of the surface, and they are perpendicular to the surface, which is kind of very nice. Okay, dokie. And if I wanted to make, for the sake of visualization, if I wanted to make those bigger, I could just take the vector and set the amplitude to a larger value and then visualize that larger vector. I don't know, just for visualization. Okay? Wonderful. So I have the perpendicular vectors to the surface. Then the next thing that I need to do is I need to calculate the distance to, I need to calculate the angle with a sun object. So for that, I'm going to have to model the sun. How are we going to model the sun? Like a big fat sphere? I mean, we could do that, but it's a little pointless because at the end of the day, what we're interested in is where the sun is in 3D space. And for that, the only thing that we need is actually a point. With a simple point, we can model, theoretically, we can model where the sun is. So I'm going to create a point here that I'm going to create in Rhino. And then I'm going to bring that point here into Grasshopper by adding an empty point component and then just loading it into Grasshopper, okay? Then the next thing that I need to do is for each one of the points that I have here on the surface, I need to calculate the incidence vector from the sun to each one of those points. So that's going to be as easy as taking a vector and creating a vector between 2 points. The first point being the sun, the virtual sun that is defined by this point, and the second point being all the centers of the planes that I have deconstructed before. So those are going to be the origins here. And as soon as I do that, I have my vectors, and just for the sake of visualization, I'm going to use a vector display. The vector display is going to visualize all these vectors and is going to anchor them on the first point. So on this point, on the sun, we're going to see all those vectors hitting the surface of hitting the points of the surface. Can you see that? Beautiful. And then the only thing that we need to do is we just need to calculate the angle between these two. We could do hardcore vector algebra for this, but Grasshopper gives us an easier way to do that, which is if you go to vectors and you go to vector here, you can calculate the angle between two vectors. So that is going to be the angle between two vectors is going to take A and B, the first and the second vector, and an optional plane if the angle that I want to measure is in a particular 2D plane. Otherwise, the angle will be in pure 3D. So I'm going to turn all of this off, and then I'm going to measure the angle between the incidence and the amplitude here. Sorry, not the amplitude, sorry, the C vectors here. And then this is going to give me a set of angles that are going to be roughly about this. These are angles in radians. So if I want to see those in degrees, I can just go to the Math tab and go to Trigonometry and then turn an angle from radians into degrees. So this will be these angles here. Now, one interesting fact is that all the angles are larger than 90 degrees. Can you see this? And it is so because if we go to the diagram, we can see that the angles that we have here on the right-hand side, where are the angles? We can see that I've actually made a mistake in the way I have drawn the angles on the diagram, because if you look at this diagram carefully, the sun is a vector that is coming this way, right? Sorry, the sun is a vector that is coming this way, which means that the actual vector is something like this. And the angle between this vector and the normal is this angle here. So that is the real omega. Whereas here, if this is the sun, this would be the real omega, which is smaller, and this is going to be the real omega, which is even smaller. So because that's the case, this is the real angle between them. And then the rule in this case will be that the smaller the angle we have, the larger we want the opening, and the bigger the angle, like in this case, then the smaller the opening. All right. So it's always good to look at the numbers and to review, because you can see that I made an assumption that wasn't really correct as from a diagrammatic point of view. All right. So what are we going to do this? What are we going to do with this? Well, what we now want to do is we now want to use this information, the angles, to make decisions about how big the circles that we're going to place on these openings are going to be. So I'm going to, for example, I'm going to start by drafting what this is going to look like. So I'm going to place some circles, and I'm going to place the circles here on the surface frames. Okay, so because the circles take a plane in order to get drawn, you can see how the circles are kind of aligned with the surface. So that's one thing. And I can see that if I drop a slider here, I can control uniquely the size of each one. But that's not what we want. What we want is to use those values, the values of the incidence of the angle. We want to use those values to affect how some of the circles are going to be bigger and how some other are going to be smaller. And before I keep talking, let me actually try how I'm going to do this. Otherwise I'm going to be rambling back and forth and it's not going to be great. So if I plug this in here, we can see that, and if I multiply by a factor, for example, this one and this one and this one. So if I reduce this, we can see that the incidence is actually quite small. So you can see that I am getting the opposite effect. So these are bigger and these ones are smaller and these ones are bigger again. So what I need to do is I need to come up with some numerical rule to change this. So how is that going to be? What numerical rule can I write that is easy to explain and that is not very esoteric? So so what I can say is, so if I plug this in here, you can see that these are bigger and these are smaller, and I want the inverse of that. So what I can do is I can I can turn all those numbers into zeros and ones based on how perpendicular they are to the surface. And I could use a diagram. So, I mean, I could map these numbers, remap numbers from value to remap is going to be this, and the domain, the source domain is going to be from what? From 0 to pi? Is that what we're doing? From 0 to pi. And then what we want is to from 1 to 0. And then I can use that. And then that works pretty well. And then we can just factor this up or down. But remapping, well, I can visualize how this works very nicely. So I can just say, I could put this here. I say the bigger the number, the closer it gets to 0. And the smaller the number, the closer it gets to 1. Huh. Maybe I could do that. I wonder if there's a way to do this numerically that is easier to explain and not so abstract as remapping. Uh, hmm. I guess I'm going to have to explain it that way. Let's explain it that way, and that's it. Where was I? Hmm. Okay, so let me just jump here. Okay, so what we're going to do is we're going to do a very simple numerical transformation so that what we're going to do is that we're going to normalize all the values of those angles into numbers that go from 0 to 1. And this process is typically called normalization, and it's a very useful process because once you take a collection of numbers that can have some range, and then you shrink it or you expand it to be within 0 and 1, working with these numbers is typically much easier. So for example, let's take a look at the possible scenarios that we have with the sun incidence. So let's say we have a facade that was purely circular, okay? Something like this. And then we have the sun that is hitting this way. What possibilities can we have? Well, if we have a point here, right, on this facade, and the sun is hitting this way, and the sun is hitting this way, then the incidence vector looks something like this. So that's the vector. And then we have here the normal vector sticking out, so the angle is going to be 180 degrees. Okay, so that is the worst condition that we can have, which is when the sun is hitting exactly the facade in the most frontal way. Now, we can have some intermediate point here, and then the sun is hitting something like this, and then the normal is something like this, so maybe this is 135 degrees, I don't know. Then we have the intermediate scenario, which is that the sun might be hitting in a tangent way to the facade, okay? And then what we want to do is we want to look at the normal and say, well, this is 90 degrees, okay? So that is the best possible scenario, which is that the sun is not hitting the surface whatsoever. It's just perfectly tangent. And then on top of that, we actually have other scenarios, which is if the building is cylindrical or spherical, we have this situation which is not really exactly like this. The sun is never going to hit this face, but from a computational point of view, we do have this in the data set. So that would be 45 degrees, and then this point here would have the sun here, and would also have the tangent here, and then this angle would be 0 degrees. So what we want to do is we want to make sure that we account for all these possible scenarios. And then we want to have a rule. We want to write a rule where if this is a situation, we have a 180 degree incidence, so purely strictly perpendicular, we want to associate this to the value of 0.0. We're going to call that the opening factor. And then if the sun is hitting the surface at 0 degrees, so completely perpendicular in the other direction, that is going to be the best case scenario, which is 1.0. Okay? So which is going to correspond to this. And then any angles in between that are going to have intermediate values. Like for example, this would be 0.5, this might be 0.75, and this might be 0.25. The idea is that with this, oh, sorry, no. So it would be the other way around. So this would be 0.25 and this would be 0.75. Yes, the idea is that what we want for ourselves is to come up with a numerical range that is easy to manipulate. And this is very typically from 0 to 1, and therefore we can fit that into other kinds of calculations. And this factor, 0 to 1, is basically telling us how perpendicularly the sun is hitting our surface. So once we're able to generate that number, which we're going to do with a very simple operation, then we will be able to use that number to derive the openings or the closings of the facade windows. Let's take a look at how to do that. We're going to go back to Grasshopper, and then we're going to take all these angles here. These are the angles, and instead of from 0 to 180, they are going from 0 to pi, because they are in radians. So we can work with, we can convert them in degrees if it's easier, or we can work directly in radians. Let's work directly in radians because we've done we've done like degree conversions already for a little bit. So the way we're going to do this is, remember, we want to rewrite this so that numbers from 180 to 0 become numbers from 0 to 1. In a way, we're also going to flip the order, okay? So we can do that with a mathematical operation that is called remapping. How does that work? If we go to math and we go to domain, we have a component here that is called remap numbers. And the way this works is that it takes several things. It takes the number you want to remap, but then it takes what is the source domain, so what is the range that these numbers are coming in from, and then T is going to be what is the domain that you want to change these numbers to. So as we said before, we're going to create here a new first domain, and the input domain, as we said, are the angles between 180 and 0. So what we want is, we're going to go here and we want to say the input domain is going to be a value that is going to start at 0 and is going to go to the value of pi, because remember, we're going to work in radians. So pi actually has its own component here. This component gives us the value of pi or a factor of pi. So we want to remap our numbers, and the domain, so the range, the interval at which they are, is from 0 to pi. That is going to be the input. And then what we want to do is we want to say the target domain needs to be a new domain. Sorry, I'm going to construct a new domain, and the new domain is going to go from 0, it's going to go from 1 to 0. Because remember, when we are at 0, sorry, oh, I'm making a mess out of this. Sorry. Sorry, when we go from 0, and when we are at 0 degrees, we want a factor of 1. And when we are at 180, we want a factor of 0. So that's why when we are at 0 degrees, we want a factor of 1. But when we are at pi radians, we want a factor of 0. So that's why we're doing this here. And then what we're going to do now is we're going to remap all of these values. So these are the values that we want to change from the two different domains. And let's take a look at what that looks like. It looks to me like this is working because the higher the value in radians of the angle, the smaller the factor. So you see how the angle becomes smaller and the factor becomes larger. And when we are at 1.5, which is more or less half pi, we are at 0.5, which is half away to the factor. So this is great. So I think we are in a good position now to plug this into the circle and see if this works. So let me turn on the angles and the vectors. We have the sun. I moved it a little bit farther, closer to the surface, so that it was easier to see that this part here was very frontal. So this part here is very frontal. and this part here is rather perpendicular. So we can see that here in this area the openings are larger than here in this area, which is a bit more frontal, where they are closer. And this area is very, very clearly super frontal to the point, and therefore the values are very small. But how big or how small? Well, right now they go from 0 to 1, literally, because it's the remapping. But if we wanted to factor those, I can just multiply those values for some kind of arbitrary value. So for example, I can just open up this and make them twice the size, for example, or make them 3 times the size, or 4 times the size, or anything, you know? So, and then now with these circles, what I can do is I can create, for example, a planar surface, which is somewhere here. Where is this? I can't see it right now. So, planar surface, boundary surface, for example, here. And then I can get that, and then I can just hide this. I can hide this surface here, and then I can remove these two, and then I can also hide this surface, and you can see how the openings for this facade are now corresponding to the angle. And if I move the sun, you can see how these guys, these windows are becoming bigger, these are becoming smaller, you see? And you see how now these windows are super big and these ones are much smaller, right? How awesome is that? And now we have a facade where every window has a size that is exactly fitted or optimized for the best sun incidence. Well, that's a huge statement, so it's not as simple as that. There's a lot more calculations, but this is the basic core of this is the basic gist of the problem. Okay. All right, wonderful. So that was designing a facade that has some kind of optimization for solar incidence. I see we got a little spaghetti-ishy here, but with a little bit of cleaning up, this can be much more legible. And of course, we can always like more count, less count, more in one direction, more in the other direction, etc., etc. So that can be parametrically customized. All right. Wonderful. So I hope you enjoyed this exercise. This was a parametric solar facade. This was Jose Luis. This is Parametric Camp. And this is the series Introduction to Parametric Modeling. Let's move on to the next video where I'm going to do another exercise that is also going to involve some kind of solar analysis / being aware of where the sun is and try to optimize some kind of orientation. In the meantime, if you had fun, if this was helpful for you, maybe consider liking this video, subscribing to the channel, and all those things that we do these days on YouTube. Thank you very much, and see you on the next video. Bye. Okay. Okay. So how am I going to tell this story? Okay, then this is going to be... All right, so let's record the introduction then. Hi, this is Jose Luis, and welcome to another video on this series Introduction to Parametric Modeling, where this video is going to be a hands-on exercise on creating a facade that has some kind of design that involves optimization for some kind of environmental parameters, such as, for example, the incidence of the sun. Because as far as we have done so far, we know how to take a surface and then subdivide that surface into a grid of elements and then populate it with, for example, a set of circles. The circles could be, for example, openings. They could be the windows of a hypothetical facade of a building. But this building these openings could actually be somehow optimized for a particular condition. Like, for example, the incidence that an external agent, like the sun, could have over this facade. Because what we can do is we can calculate how the sun is hitting each one of the points of that facade. And based on that calculation, what we can do is we can optimize some of the openings and change their size so that the ones that are directly frontal to the sun are smaller. Let's imagine this is a warm climate. And the ones that are somehow tangent, kind of tangent to the incidence, they have a bigger opening. And therefore, we can now design a facade that as we change where the sun is, then the openings adapt. This could work for the design of a facade, or it could work also for a facade that has windows that open and close throughout the course of the day. I don't know. There's many applications that we could do about this. So we're going to create this kind of facade that is parametrically adapted to the incidence of the sun. And you're going to see that the exercise is actually going to be super simple. It's a very small one. It just involves a little bit of thinking ahead. What does sun incidence mean in terms of geometry? It's going to be super simple and a lot of fun. Let's get to it. Let's get hands-on. All right. Okay, so that was the first one. And let me close the window because the sun is actually hitting me in the face. And let me open the window because it's also kind of stuffy in here. Yoo-hoo! How's everyone holding on? NT Salvador, hello. Good afternoon, sir. Good to see you. Woohoo! So, what are we doing today? What is the next thing we're going to do? Oh, solar panels oriented to the sun. Okay. How are we going to do that? Oh my God. Let me sit down and think this through. And before we do this, let me save these files. And let me save this file, save this. Let me save these files and create a new file here. What do I want to do? What? What is going on here? This one, huh? This is kind of what I want to do. Hmm. Solar thermal power stations. Huh. Uh, all right. This solar plant is actually very close to my hometown in Spain. And this is not a rendering. This is real. It's kind of cool. Mm-hmm. Good to see it. Okay. So solar panels oriented to the sun. Mm-hmm. Okay. Mm-hmm. Okay, so this is going to be. Oops, it's going to be. Oh, where is? Hmm. Okay. Hmm. All right. So let's go here. Let's save this. Let's create a new one. And okay, so how are we going to do this? The way we're going to do this is first we're going to create a grid, and then we're going to create like this basic shape of each one of these elements. We're going to create the sun, we're going to calculate the incidence, and then we're going to get all those vectors. And then I think we can explain this. Okay, so let's draw some stuff. Mm-hmm. These are going to be the base points. Too far away. These are going to be the base points. Going to be the base points. These are going to be the base points, and then we're going to create some kind of yeah, something like that. for example, and then something like this, and something like this, and something like this, something like that. And then after that, we're going to calculate the sun, and the sun is going to be somewhere here. And what we care about from the sun is actually the center. And then what we can do is we can calculate from the sun to each one of these points. There's one of this. And then each one of these. And then after that, what we will want is something like that, for example. For example, okay, so that's how I'm going to explain the project. And I'm going to use this image to explain okay. Wonderful. Let's get started. So before we start anything, I would like to set some context. What we're trying to do here is we're trying to mimic some kind of power plant of sorts where we would have a lot of solar panels, and those solar panels are going to be actuated. They're going to have some kind of motors so that across the day, as the sun keeps moving, the panels are going to orient themselves to always be as perpendicular to the sun as possible so that they can capture as much energy from the sun. This exercise was inspired by a solar thermal energy plant that was actually built many years ago next to my hometown in Spain. This is not exactly what we're doing, because what this one does is that it takes the sun. The panels here are not electrovoltaic panels, they're just mirrors. And what they do is that they mirror the sun and they concentrate it here in this point. And therefore, this point becomes extremely hot. It boils water on a turbine, turbine. It boils the water of a turbine, and then the turbine produces electricity. Okay, so this is not exactly what we're doing. What we will be doing is just more like, imagine like a sunflower. What we want is like a panel that is always moving and is always orienting itself as close, as perpendicular as possible to the sun to capture as much energy. And how are we going to do that? Well, at a basic level, what we're going to do is, by design, we're going to create a 2D grid of objects. Then we're going to elevate them a little bit from the ground, and then we might put some cones or not, just for visualization, as in this is standing on top of something. And then at some point, we will have a sun object, similar to the one that we had in the previous video. And we will perform calculations about the incidence that each one of the panels is receiving from the sun. And after that, what we want to do is we will have to come up with some way of orienting a rectangle that is going to be centered at these points that are elevated from the floor, from the ground. And the orientation of this rectangle should be as perpendicular as possible to the sun. So before we actually get into the problem of the orientation, let me build the basic infrastructure. Let me build the grid of points, etc., etc. And let's do that together, and then we can come back and we can break the problem of the orientation. Let's get started with that. Okay. Okay. Why? I could just copy. And then the Y. All right. Okay. Should I just I'm going to go fairly quick over this one because we've done many examples of this in the past. So I have a point that I'm going to bring into Grasshopper, and it's going to be the corner of my grid of solar panels. And I have sliders for how many panels do I want in each direction and the distance between these panels in the X and the Y direction. So what I'm going to do now is I'm going to create an XY plane that is based on this starting point, and I'm going to copy this plane in the X and the Y direction. So I'm going to create a series that is going to start at 0, that is going to have 10 elements and steps of 10. I'm going to create unit X vectors with this, and I'm going to use this to move the points along the X directions, and therefore creating a 1D grid of these planes in the X direction. And then I'm going to copy and paste this, and I'm going to have a similar series where I'm going to create unit Y vectors that I'm going to factor or increase by these numbers, and then I'm going to now move these geometries by these ones. But because the structure of both is the same, I'm going to graft this tree here before I plug it into this one here. Okay, wonderful. Now we could have done this on top of an actual surface, and that would have been interesting, actually. I wonder if we want to do that. Huh. Okay, we're going to cancel this. Yeah. Let's do this on top of a terrain. It's kind of nicer, no? Let's do a 2D patch and imagine that we have a terrain, and then we're going to do this on top of the terrain. Why not? Since we can anyway, right? Just it will give it a nice touch. So yeah, so let's nix this, and then what we're going to do is we are going to create a surface that is going to go from here, and then it's going to and then another one. And I'm going to, and okay. And then, okay. All right. Huh, I like that. And then we have a surface. We have a surface, and then set one surface here. And then we're going to subdivide this into frames. And that's going to be the number of frames in the U direction and the number of frames in the V direction. Yeah, this surface is a little twisted. I wonder if we could project. Yeah, because this is a little too much. This is too curvy, I think. This is not going to be nice. It's not going to give us a nice distribution. So, rebuild. And let's see if lofting this now gives us a more, yes, nice. Okay, and then let's bring in this surface. Okay, much better. All right, so we're going to hide this. We're going to hide the curve. We're going to hide the curve. We're going to hide the curve. And then we only have this left here. Okay. Okay, this is cool. Okay, this we don't need anymore. All right. Okay, so let's get started. For this one, we're going to go a little fancy, and instead of just like a flat 2D grid, we're going to work as if we were on top of some kind of undulating terrain. So I've made this surface on Rhino that I've done by lofting 3 curves, and I'm going to bring this surface into Grasshopper. And what I'm going to do is I'm going to click on the surface and I'm going to hide it so that we only get the pre-visualization here on, or actually I don't know, I want to do that so that we only get the pre-visualization in Grasshopper. And then what I'm going to do now is I'm going to take this surface and subdivide it into frames so that we get the subdivision of 10 units in each direction and 10 units in each direction, or less of them. All right. Now what I would like to do is I would like to create some kind of mast on top of this, as if it was a line of sorts or a cylinder. So what I could do is, in order to do that, I could just use the normal of the plane on top of the surface. But it turns out that when we're building things on terrains that are not even, we don't really build things inclined. We always keep the pure vertical against gravity. So in this case, keeping the normal would not make a lot of sense. So I'm just going to create on top of each one of the planes that I've created, I'm going to take the points, the centers of those planes. So I'm going to deconstruct the plane and get all of those points. And then what I'm going to do is I'm going to move those points up in the Z direction a controlled amount. So I'm going to move, these points here in the direction of Z. So that's going to be a vector in the Z direction, but an amount that I'm going to control. So that's going to be, for example, the height of these elements, for example. And I'm going to make that much smaller. So for example, 2 point something. And then maybe what I want to do is I want to join these two by lines. Maybe I can do something a little fancier later, but I can join the base point and the top point with lines. And you can see that now is one of those situations where I actually don't want to respect the curvature of the surface. I just want to keep the pure vertical here. All right. And it will be these points, the points that I've moved in the Z direction. It will be these points that I will want to use for the calculations of sun incidence. So let's take a look at that. So the first thing that I would like to do is I'm going to create a point, and I'm going to move that point, and I'm going to move it somewhere here, for example. And that point is going to be like the point for the sun. So I'm going to bring this point here, right click, set one point. And then after that, I'm going to calculate, I'm going to turn off this, and this, and this I'm going to keep. What I'm going to calculate is the incidence of the sun on top of each one of these points. So I'm going to do that with a vector between 2 points, and the first point is going to be the sun point, and the second point is going to be each one of those points that I have here. And just for visualization purposes, I'm going to drop here a vector display, which is going to visualize all these vectors from the sun, and the anchor point is going to be the sun itself. So I'm going to do that, and then I'm going to have this incidence. Okay, so let's take a look at that. Now I have the incidence of the sun, and what I want to do is I want to draw some rectangles or some planar rectangular surfaces on top of these points, center on them, so that I can orient this to the sun as perpendicular as possible. The idea is that for creating planar square surfaces, for example, if I go to freeform, there is no actual rectangular surface here. One of the easiest ways to do that is to actually go to curves and to go to rectangle. And then with this, we can create rectangles that are centered on top of our base plane, which means that, and then after that, what I can do is I can do a boundary surface so that that surface becomes an actual surface, a closed surface. So what I'm going to need, as you probably suspected already, is for each one of the rectangles that I want to place on top of these points, you see, for each one of the rectangles that I want to place on these points, this is not going to be good enough. I'm going to need to create some kind of plane where the plane actually has the orientation that is as perpendicular as possible to these vectors that I have here. And how am I going to do that? Let's take a closer look at that, and let's go back to the sketching board. Let's go back to the sketching board. How am I going to... One of the simpler techniques that I can use for generating these planes is going to be the following. Since I have a vector that is going from the sun into each one of the planes, what I can do is I can take that vector and I can flip it around and, for example, make it a vector that is pointing in this direction. And what I can do is I can generate a plane that is using that normal as the main direction of the plane. And then taking that plane, I will be able to generate the rectangle. We're going to try this. This is not the way we're going to go for the reasons that you will see very soon, but let's try this out. If we go to Rhino, what we can do is we can take these vectors, for example, that we have seen are the ones that are coming from the sun, and then we can just reverse them. We can flip them. So I'm going to take this, I'm going to go to vector, and I'm going to reverse these vectors. Okay? And as I do reverse those vectors and I visualize them, you can see that the vectors, which are still anchored in the sun, now they're facing the other way around. Well, so if instead of anchoring them in the sun, now I anchor them on top of the masts of these panels, then you can see that all the vectors are now pointing to the sun, correct? And then it turns out that if I go to plane, there is a component that is able to generate a plane that is perpendicular to a vector. How convenient, right? How awesome is this? Shall we try this? Let's give this a try. So I'm going to place plane normal here. And then what's asking me for is the origin of the plane, which are going to be these points here, all the masts, okay? And then the C is going to be the normal, which I already have here as this. And then as I do that, I'm going to turn this off, and I'm going to turn this off, and you can see that I have a lot of planes that are kind of oriented towards the sun. Is that correct? And then as I plug those in here, you can see that now all these panels are now looking at, are they looking at the sun? So am I the sun? Yeah, they look like they're looking at me, right? Let me turn this on just to make sure. It pretty much looks like this is working. You can see how each one of the panels is facing directly towards the sun. Let me move the sun like really close to the ground to see if this is true. Let's see. Let's even bring this closer and closer. So you can see how now we have this kind of like concave sort of, yes. So this is great. Okay, so this is great. It's working. The panels are perpendicular to the sun, but can you see something not totally okay here? Is there something that we could improve? Give it yourself a minute to think about it. I'm going to give you some time. I need to improve my time passing kind of, you can pause the video and give it some thought. But otherwise, what I would like to point out is that the problem with the technique that we have used is that this component, the plane normal component, is a component that is able to generate a plane that is perpendicular to a vector. The problem is that the solution to that problem is infinite. The solution to the problem of a plane that is perpendicular to this vector, for example, might be this one, might be this plane here, but it's also this plane here, and it's also this plane here, and it's also this other plane here, and it's all the possible planes that you can have rotating a plane around a vector. So there's infinite solutions, and Grasshopper just chooses one arbitrarily with some kind of rule that we're not really sure of. And if we were on the field, typically this would not be a solution for us, because what happens typically is that these elements, what they have is they have a mast, and the way they can rotate is they can perform a rotation around the mast, and they can perform rotation perpendicularly to where the mast is. So this kind of solution is not going to work for us. And in order to get a solution that is more realistic with the real world, with two motors or two axes, one the vertical axis and the other one doing this, we're going to have to do a little bit of vector manipulation and vector analysis to fine-tune this solution. Are you ready for that? It's going to be super nice, super fun. Let's take a look. Okay, so solar panels, and this one is going to be solar panels. And before we do anything, I'm going to try out, how can I do this? I had the example written somewhere, but I've lost it. So how can we do this in a way that is comprehensible? So the first thing we need to do is we need to, from the top, so if this is X and Y, we have the mast here, we have the sun incidence, we need to figure out what is this angle here? So that the x vector of the plane is going to be in the xy plane and is going to be rotated that angle. This vector we can find by doing the perpendicular vector between the c vector here and this one. So that would be this vector here. And y is going to be this one. It's going to be a vector that is going to be perpendicular to this one and this one too. So how do I do perpendicular vectors here? How do I do that? Is there any component that does perpendicular vectors? Or, I mean, I can use the cross product. I just don't want to get into the weeds of explaining the cross product. Does it explain here? Compute the vector dot product. I could calculate I could create a plane between, so if this is the sun, if this is the mast, and this is the vector, I could create a plane that is vertical and that follows this direction, and then the c, the normal, is going to be this one. And then I can do another plane that is going to be, this is going to be x, this is going to be y, and then the perpendicular is going to be this one. Maybe I can explain that. Let's try explaining it that way. Let's try explaining it that way and see where it happens. See where it goes. Okay. How am I going to explain this? We have the main point here. I'm not going to do that. I'm just going to, or maybe I can use my favorite brush now. Wait, so no. Yes. Well, this is a lot. Okay, so actually this is a lot. Let's just do gray. Let's just do gray. Okay, so we have that. And then, before that, we have that. And then let's make a Cartesian. Let's make sure that we know that, oops, not this one, that this is x. So let's make sure that we know that this is y, and let's make sure that we know that this is z. Okay? All right. So we have that, and then we have the sun hitting, we have the sun, which is coming somewhere here. Somehow. Okay? And then we have the perpendicular vector that is sticking out of here. So we know what we want to say is that the first vector needs to be somewhere in the x and y plane that is formed on top of this center. And then if we take these two vectors and we find a vector that is perpendicular to these two, that will give us the rotation in plane. That will give us the rotation in plane. And how can we do that? We can do that by just creating a new plane that is going to be aligned here, which is going to take the main x is going to be this one, and the other one is going to be this one. And therefore, the c of this plane will be that first vector that we want to figure out. And that I can draw myself, for example. Let's try to explain that. Okay, so let's do that. So the first thing that we're going to do is we're going to take a closer look at the tip of this mast, or the center of where do we want to set ourselves the plane that is going to be the base of the rectangle for the panel. And if we take a closer look here, we know that we have a point at that top, and we know that we have a ray that is signifying the incidence of the sun. And what we want to do is we want to find here, somewhere on the xy plane that is on top of this plane, horizontally, what we want to do is we need to figure out a vector that is somehow perpendicular to the combination of I am making a mess here. Okay. Let me start over again. Starting over again. Let's take a closer look at the tip of one of these masts, or in other words, the center of where we're going to place the plane that is going to be the reference for the solar panel rectangles. If we take a closer look here, we have a few elements. The first element we have is the ray that is coming from the sun, is this vector that is telling us the direction of perpendicularity. And the other element that we have is that we know that the mast is pointing, is sticking upwards. So we have a vector that is somehow perpendicular to gravity. Okay? Now, what we want to do is, because the first angle that we want to find is the angle of rotation of the mast, like this, because this, we know that this is the first servo, one of the motors that the panel has. What we want to do is we want to figure out in a imaginary xy plane that was centered here at the tip of the mast. What we want to do is we need to find a vector that is perpendicular to the plane that is formed by these two vectors. If this vector, the perpendicular vector, and the sun vector, they both form a plane that we can find the perpendicularity for. And the perpendicular to that plane is going to be this one, and that's going to give us the angle that we need to rotate the mast to compensate, to approximate to that, to the sun incidence. And how are we going to do that? Well, we can actually create a plane, for example, that is going to be centered here at this point, and the main orientation of the plane might be this c vector that we have. The other orientation of the plane can be the vector, and then that plane that is containing the two vectors, the x and this that is containing the origin, the normal vector and the sun vector, that plane, the perpendicular to that plane, the normal, this one, is going to be the vector that we're looking for, is going to be the first vector that is going to serve us for the plane. Okay? So let's take a look at how to do that in Grasshopper. So we were here, and I'm going to remove like all this stuff that is not really working well for us. And I'm going to take the sun and I'm going to move it somewhere farther out here, okay? So that things are a little clearer. And I'm going to remind us that we have the vector that is pointing towards all these points, okay? Now, what I need to do is I need to be able to create a plane that it contains a plane that contains this vector, a c vector, and the vector of the sun. All right? So the way I'm going to do that is I am going to create a new plane. What is a new plane? I'm going to create a new plane. And how am I going to create this plane? Now, the way I'm going to create this plane is by constructing the plane, okay? And then I'm going to use as the origin, I am going to use the points, the center points. Then the main x vector, as we discussed, is going to be a simple c vector that is going to stick up in the c direction. So I can just use a simple unitary z vector, no more complications. And then the y vector is going to be a vector that is going to be the sun vector. And then as we do that, you can see that these vectors these planes are now all oriented towards the sun. You can see that they include the vertical and that they also include the sun ray inside of them. And then you can see how their perpendiculars, their normals, are perpendicular to this incident. So let me deconstruct this plane so that I can get those normals and I can visualize those normals as well. So I'm going to display, I'm going to do vector display, and I'm going to display from these origins, I'm going to display the c vectors. And you can see how we are finding the vector that is perpendicular to the plane that is formed by the mast and by the sun rays. Okay, so we have those vectors ready, and then we need to figure out now what is the other vector that we need to find in this series of relationships. So let's go back to the drawing board. Okay, this angle that I've drawn it's really bad. So let me just draw a new vector, a new red vector. And yeah, well, I mean, it's very difficult to draw in a way that is not, because yeah, it kind of looks like this should be like this, right? Okay, well. Okay, so let me just draw another. So what I need to do is I need to figure out another vector, and this vector should be perpendicular to these two. All right? So what I need to do is I just need to create a plane that is contained something like this, and where the main vector is this one, and where the second vector is also pointing towards the sun. Oops, sorry. And the second vector is pointing towards the sun. And then what will happen is that the perpendicular vector, I can do that with drawing, will be that one here. And once we have that, this will be the two vectors of the plane that I will use to... Oh my god, that was terrible. Oh no. I guess. Okay. Okay, so I think we're ready to go now. So as we have seen before, we now have this vector, the vector that I can't draw on. We now have this vector, the main vector x of the plane that will contain the panel. And now, but we now need to find the vector y that will be the secondary vector for that plane that will contain the panel. And that vector, the vector y, is going to be a vector that is going to be perpendicular to the two vectors that I already calculated. One, the one that I just calculated that is perpendicular to the sun plane, and the other one, which is going to be the sun incidence. So this vector is going to be perpendicular to that plane, and therefore what I need to do is I just need to create a secondary plane that is going to have two main axes. The main axis is going to be oriented towards the vector that I just generated before, and the other one is going to be oriented towards the sun. So as soon as I do that, then it's going to be very easy to understand that this vector, the perpendicular vector to this plane, is going to be the y vector for the panel that I am looking for. And once I have those two vectors, I can generate now a panel, a plane that is oriented perfectly towards that surface, towards the sun, sorry. So let's take a look at how to do that in Grasshopper now. So we said that we need to generate a plane that has the main direction x pointing towards the vector that we generated before, and the secondary direction, y, pointing towards the sun. So let's construct another plane. The origin is going to be the same point, the point at the tip. The x orientation is going to be the vectors that we just found before. So those are the normals here. So those are these vectors. And y is going to be the sun vectors. So where is the sun? Where is the sun? I forget where is the sun. The sun is here. Okay, so that's going to be this one here. And then if we do that, we can see that now we have all these planes. And just like before, what we had were vertical planes that were containing the mast and the sun. What we have now is this kind of horizontal planes that contain the sun ray, but at the same time have the perpendicularity that we calculated before. So let me, just in case, deconstruct that plane and discuss and show the vectors. So as you can see, I'm actually going to turn everything off. And now you can see we have the x vector and we have the y vectors. So can you see how this is super nice now? We have a family of 2 vectors per mast. One is the x vector and one is the y vector. And all of them are distributed equally and are going to be super, super useful to now create to now construct the final plane, which is going to be centered around the tips of the masts. The x vector is going to be the one that we just calculated here, and the y vector is going to be the one that we calculated here. And then I'm going to shut this down, and then we're going to see that now all the orientations are going to be consistent. So for example, where was this rectangle? Here, you can see how now, let's give this some, and now I can do boundary surface and then poof, just get this straight. All right. So how much nicer is this arrangement? So now you can see that all the planes are, you can see how they're basically rotating in one axis and then also inclining in the other axis. You see, as opposed to what we had before. Let me show you what we had before, which was planes that were created from a normal, and this was the center and this was the sun. And then, so this was one alternative, the bad one. And then we used this to you see? So these are planes oriented like who knows how or why, whereas these are the ones that have like a consistent orientation now, which is super, super nice. So let's add a little bit of parameters here. So I'm going to add, for example, the size in the x direction, the size in the y direction, and then you're going to, you remember how I have the expression, and this is going to be, for example, the dimension. This is going to be the dimension, and then this is going to be minus 0.5 times the dimension. This is going to be minus 0.5 times the dimension. This is going to be positive 5 times the dimension. This is going to be here, and I'm going to construct a domain. I'm going to construct a domain between these two, and then I'm going to copy and paste this for here, and these are the dimensions that I'm going to use for the panels. So this is going to be here and here, and these are also going to be here and here. And now I can say what is the height going to be, or what is the width going to be. And you can see that now all the panels are very nicely distributed in a consistent way to the sun. And let me hide this to make things a little more visible. And let me hide this as well. And let me hide this point as well. And now you can see that if I now move the sun, the orientation of all of them, can you see this one rotating? How nice is this one? How it's rotating, and if I move down, you can see how it orients vertically. You see? Can you see the clear orientation of the two angles? And then you can see how it's looking. Each one of them is constantly looking at the sun and only rotating in each one of the two directions. Yoo-hoo! Alrighty. So I think this was the exercise that I wanted to do. Food for thought. You can add, for example, a cone in the mass to make it look a bit more nice. You can add thickness, and you could also, from this parametric definition, you could output numerical values for the radiance of the rotations so that you could feed those into a machine, and the machine would be connected to some servos and blah, 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 and would be actually moving these things in 2D or 3D. So that could be pretty interesting as well. I think with this, I'm done with this exercise. I hope this was fun. I hope the whole vector manipulation and the angles was not very confusing, but this kind of work is a lot of the work that we typically do when we're trying to analyze the orientations and the angles of things in 3D space. And long story short as well, I have worked here with creating planes that contain two vectors just for the sake of finding a perpendicular one to them. This operation would have been much easily done by doing an operation that is called the cross product of two vectors, because one of the properties of that operation is that the cross product of two vectors gives you a vector that is perpendicular to those two. So, but we didn't get into that. We're not going to get into that in this series. So I just decided to keep it easier with planes, for example. And that's it. I think, yes, that's going to be it for this exercise. Thank you very much. Thank you for staying here. If you learned something or if you want to show some gratitude, feel free to like this video or subscribe to the channel or any of those, or leave a comment or extend this exercise to make it cooler, whatever you want to do, okay? It's up to you. So this is going to be the exercise, and yes, I'm not going to show that. Am I going to show that? Yes, I'm going to show that. All right, cool. Thank you very much, and see you on the next video. Bye-bye. This is kind of distracting, actually. I'm kind of regretting a little bit doing this. Mm. Do I want to show? Okay, so we need to record the introduction now. So this is going to be one group. This is going to be another group, another group, another group, another group. Okay. Hello, this is Jose Luis, and welcome to a new hands-on exercise on this series, Introduction to Parametric Modeling. In this one, what we're going to model is one of those solar farms that you can find outside in the country, where you have a lot of solar panels that are oriented towards the sun, and that they rotate and they move over the day to be as perpendicular as possible to the sun. So what we have here is a surface that I'm going to hide for the sake of visualization. And then what we did was we created a bunch of panels, and each one of them has a particular rotation in the z-axis, but also a particular rotation on top of its own local axis, so that it follows the direction of a set of virtual rays that are pointing to the center of that panel, and they're always perpendicular as possible to the sun. So what that means is that as the sun might be changing directions over the course of the day, then each one of those panels could potentially move and reorient to be as perpendicular as possible and maximize the efficiency of how much energy they can draw from the sun. What we're going to learn in this exercise is a little bit of, how can I say this? Looking at vectors in 3D space and figuring out how to create perpendicularity and how to figure out the right orientation for geometry generation and manipulation. So it's going to involve a little bit of 3D visualization of vectors or perpendicularities, etc. But if you are into computational geometry, I'm sure you're going to be able to handle this. So without further ado, let's get started. Okay, wow. Oh, well, I have two more exercises, the tentacle surface and the tentacle surface and the brick wall. And then we're going back to lists. So how are we going to do that? I'm a little tired today. We can probably do the tentacle surface and then we can get over, and maybe the brick wall is not so interesting, honestly. Or maybe it is, and I'm just trying to avoid doing it because it's going to be a little tedious. And so this one here, this one saving, going to create a new file. Okay. Oh, all right. Tentacle surface. Okay, so what are we going to do? All right. Where my mouse? Where is my mouse? Okay. 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 So let's draw some diagrams. So this is going to be the surface, and I'm going to, oops, no, I'm going to move it, nope, here. I'm going to move it here. And what do I want to do at the end of the day? Hey, Nightick. Hey, what's up? So what are we going to do? So the first way we're going to do this is what I want is to What I'm going to do is something along the lines of creating this, and then this, and this, and then hopefully somehow creating some kind of aperture that is going to be perpendicular, some kind of aperture that is going to be perpendicular, something like this. Oops. Something like this, and then something like this, and then I will want to join those two with a loft. And then creating a lofted surface, something like this. And okay. So that's going to be one. But this is not what we're going to do right away. Oops. So I'm just going to, what I'm going to do then is first I'm going to subdivide some planes here. I'm going to create some planes here. And then once I have that, I will use that to create some kind of rectangle. Some kind of rectangle. Some kind of rectangle. And then some kind of rectangle. And then I will create, on top of that, I will create circles. And then on top of that, after that, I will join the circles with a loft, something like this. And I'm going to now use this. This is going to be here, it's going to go here, it's going to go here, here, here. This is going to be the first step. And then we will follow a second step at some point. What are we doing here? Oh. Okay. And then, oops, sorry, here, and then okay. All right. So we have this, and then so let's start drawing. Um, okay. All right, let's get started. So, just for a little bit of context, this exercise is inspired by the Kunsthaus in Graz, the House of the Arts, which is basically this like blobby, tentacly kind of building that has these orifices or these openings that are coming out of the roof and that end in these kind of circles. Obviously, we're going to make like a way more oversimplified version of this. No crazy. We're still beginning, all right? But it's kind of where the inspiration, if I may, where the inspiration came from. So what we're going to do in this exercise is we're going to start off from a surface, and where we want to get to at the end of the day is having a situation where we would like to subdivide that surface into a set of regions, and then we would like to use those regions to extrude those regions, if you will, into circles that could be openings or windows or who knows what. Okay. Now, this exercise, as I just explained it, is going to require a little bit of additional components and logics that I haven't really explained. So before we do that, I would like to do a simplified version that is going to suck. It's going to be really not great, but this is going to give us like a warm up to how we're going to implement this in the real sense. So instead of doing that, the way I'm going to start is by a simplification, which is going to be, I'm going to subdivide this surface into a grid of UV planes, and we already know how to do this. I'm going to use those planes to create rectangles, just simple planar rectangles that are not going to fit each other, and that's why this solution is not great. And once we have those, I'm going to use those planes also to create perpendicular circles that are offset from that plane, a technique that we haven't seen yet, and then try to figure out if I can fit a surface going from those circles to those rectangles. This will be a okay situation. It's not going to be watertight, but it will be a good foundation for then creating the actual final one, which is going to be the version that I just explained before. So let's take a look at how to create this simpler version first, and then we will revisit how to generate the more advanced version. All right, bye-bye Kunsthaus. Who was the architect of that? I forget. Morphosis, one of those. Okay, so I'm going to press here. Okay. Let's start. I'm going to start with a surface that I have in Rhino because maybe you generated this surface parametrically, but maybe you were just modeling until you found, like, with your hands touching up and down these points, you found the perfect shape, right? And now what you just want to do is, on top of that shape, apply this logic of creating these windows that pop out of the surface, if you will. So I'm going to assume we have a surface in Rhino that I'm going to bring into Grasshopper, and then we're going to do the typical process of subdividing this into frames. So I'm going to subdivide this surface into a controlled amount of frames in the X direction and the Y direction. So more, less, etc., etc. And now, once we have this, what I can do is I can create, for example, a family of rectangles on top of these planes. So I'm just going to draw some rectangles here, all right? And we already know that the rectangles take domains, so we are going to create here the size of the rectangle in one direction and the size of the rectangle in another direction. And because we did that in the previous example, in the previous video, I'm just going to copy paste that here. So give me a second. So yes, so I just copy pasted this idea of taking a number and creating a domain that starts at half the number and ends at half the number. That starts at minus half the number and ends at positive half the number. So I'm going to use that to feed in the dimensions of these rectangles. So now I know that I can create rectangles that are whatever distance. And I'm going to hide this surface so that I can see a bit more clearly. Okay? Now, the next thing that I would like to do is I would like to create those circles that are going to be protruding out of the surface at a controlled distance. So how is that going to work? Well, I could use these frames here. So let me just, for the sake of prototyping, I'm just going to place some circles, and these circles I'm going to be using these frames, okay? And I will have another variable which is going to be the aperture of these circles, and that I can open and close, for example. So I'm going to make them this small. But obviously, I don't want them to be on the same plane. I need them to be on the outside. I need to be them on a plane that is perpendicular to the surface. So how do I do that? Well, it will be just as easy as taking each one of these planes and copying it or moving it in a direction that is perpendicular to the surface. And which direction is that? Perpendicular to the surface is also the direction that is perpendicular to the plane itself. So that is why planes are great. So I'm going to take the plane, I'm going to find what the normal vector to that plane is. I'm going to multiply that vector by the distance, and then I'm going to take that plane, the original plane, and move it by that vector. Let me do that here. So I'm going to take the vectors, each one of the planes. I'm going to deconstruct those. I'm going to deconstruct those planes. Okay, so I have the origin, x, y, and the normal. So now what I'm going to do is I'm going to multiply. I'm going to create another input that is going to be the distance, for example. And then what I'm going to do is I'm going to multiply the normal by that distance. And remember that by definition, planes have unit vectors for x, y, and z. So if I multiply c by 5.23, then the length of that vector is going to be 5.23 because the vector was a unit vector. And now what I can do is I can move all these planes by this vector that I just created. And therefore, I will create a copy that is offset in the perpendicular direction. So I can go here to transforms, Euclidean, move, and then I'm going to move all the frames from the surface. I'm going to move them a direction that is perpendicular to them, but and is controlled by this distance. And it turns out that the original surface was flipped. So I'm just going to show the surface. I'm going to select that surface, and I'm going to type flip so that the internal orientation gets backward, so that I can have a positive distance. And if I am correct with what I'm doing, let me hide this again. If I am correct now, you can see that these planes, indeed, they look like they're moving perpendicular out of the surface. This, and this, and this. So I think these planes are now the planes that I want to use to create these circles here. And now you can see how the circles are offset from the surface a controlled distance. Okay? Now I'm going to remove all of this and all of these planes to leave things a little clearer. All right, and then the only thing that I need to do left is to create a surface that goes from each one of the rectangles to each one of the circles. So let me show you how to do that. Because it's two curves that I already have in 3D space, probably the simplest way of doing this is by creating a loft between the rectangle and the circle. Okay, so let's try that. I'm going to create a loft that is going to go from the rectangle to the circle. And is this going to work? Let me plug the rectangle first, and then let me plug the circle second. And you can see that it's not working, and it's not working. And it's actually doing this weird thing where it's creating this kind of surface that is going through all the rectangles and then all the circles. Which is actually kind of cool. So let me bake this and take a look at this in a geometry kind of a... So let me take this and, wow, this is kind of cool. Let me see this in a render way. Nice. I kind of like this. Well, I don't know what this is, but it's kind of cool. So yes, so now let's go back to fixing this problem. So obviously this is not behaving the way we want it. And why? What do we think might be the culprit? Yes, what has Jose told us? That very likely it's a problem with data. So let's take a look. Let's use a panel to take a look at the data. Okay, so I'm going to press a panel here. I'm going to plug in here these rectangles, and I'm going to take a look at what the structure of the data looks like. It's a data tree. It has a bunch of branches from 000 to 006 with a list of rectangles inside of each. And then I'm going to compare that to what's coming into the circle. All right. So this what's coming out of the circle. The circle has a identical structure. It has the same data tree, same branches, but instead it has circles. And another thing that I recommended in previous videos is that in order to understand how this component is working, because we are plugging both inputs into the same, both wires into the same input, it's a good thing to mimic that process with a panel. So I'm going to plug in the rectangles first. That's what I did. And then I'm going to shift add the circles to the same. And what is happening is that when they both get combined, because they have the same structure with the same branch names, all the elements get combined into the same branch. And as I said in my previous videos, because Grasshopper components work at the list level, then what the loft component is trying to do is to try to create a loft between all these rectangles and all these circles, one loft. And another loft between all these rectangles and all these circles, which kind of makes sense given what I'm seeing here. I see like a surface that is kind of sweeping and lofting over all these rectangles and then wraps up and tries to do all these circles. So I think we have identified the problem, but now we have to figure out the solution. So what we want is surfaces that only join one rectangle with one circle, another rectangle with another circle, another rectangle with another circle. So if the loft component works at the list level, I need to figure out a way to create lists that only contain one rectangle and one circle. One rectangle and one circle, one rectangle and one circle. So the way to do that is, what do you think is going to be? As we said, we can do grafting or flattening. Which one of those two are we going to try? If I flatten, it's going to be worse because all the rectangles and all the circles are going to be on the same list. And when combined, I'm going to have one single loft that is going to go through all the geometry. So I need to do the opposite. In this case, I need to graft a tree for this one, and that will give me a circle per branch. I need to graft the tree for the rectangles, and that will give me a rectangle per branch. Correct? And then when I mix them together, so when I plug in here the rectangle, and then when I plug the grafted circles, you can see that because they have the same structure, when they get combined inside of branches, now I get a branch with one rectangle and one circle, another branch with one rectangle and one circle. And therefore, if I do that here, I'm going to get the rectangle, and then I'm going to shift add, and I'm going to get the circle. All right. Is that true? Yoo-hoo! It's kind of working, but not quite. What is this weird torsion that is happening in the, this is not great. I mean, could be great if that's what you're shooting for, but I kind of wanted something that it was more of a straight kind of loft, sort of, between them. So this is clearly not working. And it's not working just because lofting has a bunch of options that allow me to control how the loft is working. And in this particular case, the error that is happening is that the internal domain of the rectangle, so where the rectangle is at 0 and where the rectangle is at 1, might not be aligned with where the circle has its internal domain starting at 0 and starting at 1. Even though they're both close periodic curves, I don't know, here, their start points and the end points might not be aligned. They might be twisted like this. And therefore, if I don't tell loft otherwise, loft is going to try to create a loft that aligns the internal beginnings and the internal ends of these two curves. So how can I solve this? Well, turns out the loft component has an input called loft options, and I can generate here with loft options, I can generate an object called loft options that I can plug in here, and then I can control some of the parameters of how the loft is generated. So we can have a different kind of loft type, loose, tight, strays. We can refit the loft, we can rebuild it, and we can do something that is called adjusting the seams. I'm not going to get into all these options, but adjusting seams, what we'll do is that it will align those two, it will align the beginning and the end. So if I add a Boolean toggle here and I turn this into true, you can see that the lofts are now nicely aligned. The two curves are nicely aligned with each other. The seams are aligned. So I have been able now to generate this approximation to taking a surface and populating it with this kind of apertures that go from a rectangle to a circle. However, this is not where we want it to go, because what we want is actually watertight, nice, solid. We could not make a roof out of this. Like, our client would kill us, you know? So let's take a look at how we could change this to make it now actually watertight. Okay, let's take a look. How am I going to call this file? Oculus roof. Oculus roof. Okay, I'm going to call this Oculus roof, for example, E13 Oculus roof. And this is going to, I'm going to save this as E13. Okay, so, and it's going to be the last exercise because I'm really, really exhausted. So, so let's go back to this exercise, and now what we can do is we can divide the surface into patches. We can divide the surface into patches, and then where's my mouse? Here. Okay. We can divide the surface into patches, and once we have these patches, what we can do is we can find the center point, more or less, for each one of these. We can find the center point and then find the perpendicular plane for each one of these. So something like this, something like that, something like that. Once we got that, we can just draw circles on top and then what we can do is we can extract from each one of these patches the boundary the boundary. And then once we have this boundary, we can now create an extrusion between this. Whoa, 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 whoa. And we can create an extrusion between this. Ooh. And I'm feeling fancy. I'm going to do something like this. And I'm going to, oh no, I can't do that. There you go. There you go. Okay. Let's explain the exercise now. Woohoo! As we said before, we can start with the surface, but instead of subdividing it in frames, whatever, we actually want to be really, really faithful to the original shape of the surface. And we want to make sure that the extrusions land exactly on the surface. So in this case, we're not going to be able to just generate any square. We're going to have to work with contours that are actually exactly contained on the surface. So what we're going to do is we're going to divide the original surface into patches, so smaller chunks of surfaces that are going to be smaller parts of the larger surface. We're going to divide the surface, instead of UV frames, we're going to divide them in UV patches of surface, or I think in grasshopper terms it's called isotrims. So we're going to do that. And then after that, for each one of those new surfaces that I'm going to obtain from the original one, I'm going to find the plane that is going to be more or less on the center of that surface. And I'm going to move that plane perpendicular so that I can draw a circle that is offset from the surface. And once I have that, then what I'm going to do is I'm going to take the surface and I'm going to extract the contour lines. This time it's not going to be a perfect planar rectangle. It's going to be the lines that are the contour of these surfaces. And I will use that curve in 3D space, the curve that is the edges of the surface, to loft these openings that are going to go not from a planar rectangle, but from the 3D contour of the patches into the circles that I have created up, that I have offset from the surface. How is that going to work technically? Let's take a look. All right. Oh, so there you go here. What do we got here? Okay, so I'm going to add this to the group, and then I'm going to group this, and group this, and group this stuff, and group this stuff, and then group this stuff here. And now what I'm going to do is I'm going to take all of this and all of this and all of this, and I'm going to copy paste it. And I'm going to bring it here. So I'm going to start off from the definition that I had, but I'm going to turn off everything, and I'm just going to create I'm going to create a new version here underneath. And then this is going to start with the surface. And then, as I said, the first thing that I would like to do is I would like to subdivide the surface into patches, or I'm going to basically cut the surface into smaller surfaces, if you will. So the way I'm going to do that is with surfaces, utilities, there is a component that is called isotrim, which means that you need to extract an isoparametric surface of which says that you can extract an isoparametric subset of a surface. What does that mean? Well, that's kind of a mouthful to say that the input is going to be the surface and D is going to be the domain of the subset. What that means is that for example, if this surface was to have a domain that went from 0 to 1 in U and from 0 to 1 in V, I could say, give me the surface that goes from domain 0.2 to 0.3 in X and 0.5 and 0.6 in Y. And it will give me like a tiny chunk of the surface that is somewhere in that domain space. So, and if you can see the hexagon icon, it's giving me the indication that it's a domain, but it's not a one-dimensional domain like the ones that we have seen before. It's not this kind of domain. It's a domain in 2 dimensions, which means that it has one domain in V and U and another domain in V. So how are we going to handle this? Well, first of all, let's plug in the surface, okay? And then the domain of the subset is going to be, for example, let's do an example where we just take a tiny chunk of that surface. What? What's going on here? Oh. Mm-hmm. Okay. So yeah, I could do that, but I kind of don't want to do that because then I'm kind of cheating, and I want to show this the whole ordeal. I kind of want to show like the whole problem, you know? Uh, uh, Rolando, since this is, I hear you, I hear what you're saying, and I would totally do that. It's just that because I'm trying to, this is an educational playlist, I'm trying to get people into understanding 2D domains. So that's why I would like to break down the problem a little more carefully. So, so that's, we're going to break this down step by step. But I will want, you're right, I will want to talk about reparameterization. That could be useful, actually. Can I reparameterize this? Does it? It doesn't give me. It doesn't give me the option. And is the? And there's no. Okay, so where were we? I was saying that let's take a look at how to extract a tiny chunk of the surface. In order to extract a tiny chunk of the surface, I think one of the most useful things that we can do is start understanding what is the domain space of this surface. So for example, one way that we can do this is by taking the surface and say, can you deconstruct the domain of the surface? And if I do that, I can see how, if I plug in this surface here, I can see that U starts at the value of 0 and U1 goes till 32, and V, the domain in V, is from -1 to 0. Another way of looking at this is if I use a domain to empty parameter and I plug in the surface, you can see that the output is the U domain from 0 to 32 and the V domain from -1 to 0. So those are the range of values through which the parameter, this number that we could use to find the location on the surface, through which the parameter can navigate in the U and the V directions. So what that means is that if I want to take a chunk, if I want to cut out a patch of the surface, I have to define an interval in U and another interval in V that I can use to extract that surface. So what I can do is, instead of deconstructing, I can construct a domain in two directions from U and V parameters, okay? And then if I plug in here like a few sliders, I can say, give me a domain that goes from 4 to 10, for example, in the U direction, and give me a domain that goes from -0.9 to -0.5 in the V space. And if I plug in a panel here, I can see that I have created an interval a domain in 2 dimensions that goes from between these two values. Are these two values, is 4 and 10, are they inside of U? Yes. And is -0.9 and -0.5 contained inside of -1 and -0? Yes. So therefore, if I plug this in, you can see that I have been able to extract like a chunk of that surface that goes from this value to this value in the U direction, and from this value to this other value in the V direction. Okay, so that is a way of just retrieving one single chunk of like one patch of a surface from the overall surface. Now what I need to do is to do this iteratively, so that I make sure that I take the whole surface and I cut it in, like, for example, 3 surfaces in the Y direction, in the U direction, and 5 surfaces on the V direction, whatever that is. So what I need to do is I need to perform some arithmetic to take this domain and cut it into U's that go from 0 to 10, 10 to 20, 10 to 30, and then for V, for example, -1 to -0.7, -0.7 to -0.3, something like that. So that would be quite tedious to do manually, but thankfully Grasshopper has some options to do that. So there is one component here on the domain, divide domain, that is called divide domain in two dimensions. And what this component does is it takes a domain in 2 dimensions and it divides it in a set of segments in the U and the V direction. How convenient is that? So I'm going to take this, which is a domain in 2 dimensions, I'm going to plug it in here, and I'm going to divide this into 2 segments in the U and 2 segments in V. And if I copy paste this, you can see now that this component has given me 4 domains. Or if I do this, it's going to give me 9 domains, which go from U000 and then 3 versions here, 3 divisions for U and another 3 divisions for V, and 3 divisions for U and 3 divisions for V. So if I now take all these 2-dimensional domains and I plug them into isotrim, what I get is this nice subdivision of the surface in 3 patches in one direction and 3 on the other, or more or less. But we're doing this numerically by subdividing the domain space of the surface. Okay? Yoo-hoo! Well, that took some time, but I mean, arguably, I think it was very interesting because we learned a little bit of 2-dimensional domains, and we also learned about like we also refresh like the internal properties of surfaces, domains, u directions, v directions, and parameters. Okay. Woohoo! All right. So we now have the the surface patches. Now we need to find the planes that are going to be at the center of those patches. How can we do that? Let's go check Grasshopper. So the way we're going to do that is that typically, perhaps in the past, we would have taken the surfaces and we would have divided them into a grid of UV frames, whatever. But for this one, we're going to go a bit more elegant because we only want the plane that is roughly at the center of the patch. So what we can do is we can analyze the surface, and there is here a component that says evaluate the surface for certain properties of a UV coordinate. What does that mean? I'm going to place this in here, and you're going to see that this component is actually giving me a lot of stuff. So it asks for a base surface. So that is a surface that I want to evaluate or get properties from, and the UV coordinate to evaluate as a point. So it's asking me for a point, but it's not a point in world coordinates. It's a point that is going to be understood as UV coordinates. So and instead of x, y, z, it's going to be u, v, and w, if you will. And then what it's going to give me is going to give me the point at that UV coordinate, the normal at that UV coordinate, the u direction, the v direction, and the frame. So the plane that will be perpendicular to that surface. So, okay, so how can I do this? Well, I'm going to plug in here the surfaces, that's one thing, and then I'm going to give it UV coordinates roughly from the center. The only problem is that if you remember, these surfaces have domains that are all over the place. So if you remember, the domains of these surfaces are now from 0 to 5 and -1 to whatever, and from -1, so it would kind of take me quite some tedious operations to figure out what the middle of U for this one is and what the center for V this one is, and do that programmatically for each one of the domains. Whereas if the domains of each one of my surfaces were normalized, if each one of the domains in the U and the V directions went from 0 to 1 for each patch, then it would be super easy for me to know that the center is going to be roughly at 0.5, 0.5, and 0. So what I can do is, let me first create a point. I'm going to construct a point that is going to be at coordinates 0.5 for x, 0.5 for y, and 0. You see that a point shows up here in world coordinates, but don't be mistaken, because we're not going to use this point as a point in world coordinates. The only thing that we need is a point that has 0.5 as the first coordinate and 0.5 as the second coordinate, because if I plug this here, it will not be understood as x, y, z. It will be understood as u and v values. And as you can see, no points show up here. I mean, they show up here, but they are all the way out there, because this is where 0.0505 of the surface is. What I need to do is I need to make sure that each one of these surfaces, now each one of the patches, has a domain that is normalized. So u and v both go from 0 to 1. And it turns out that in Grasshopper there is a shortcut to doing that. We could do that manually, but there is a shortcut here that if whatever input takes a surface, if I right click and I say that I want to reparameterize this input, what that is going to do is that immediately any curve or any surface that is reparameterized, what reparameterization does is it normalizes the domains of any direction and it sets them to be from 0 to 1. And therefore, a point more or less at the center, remember this is not the right center because of domains can be non-homogeneous, a point more or less on the center will be at 0, 5 and 0, 5. So now we have all our frames that are at the center of each one of the patches. And then now what we can do is we can follow a very similar process to what we did before. We now take this. I'm going to take and copy all of this. We're going to take the frames and I'm going to move the frames and I'm going to multiply those frames by this height here and I'm going to multiply the circle. So I'm moving the planes and I'm moving them in -y. Maybe I have to turn this into a negative slider because the surface is flipped apparently. And then I'm just going to do that like that. And then the circles are being drawn here on top of these planes. Okay. All right. So I've basically copied what I had before. So I have now the surfaces. I have now the surfaces, and I have now the circles that are offset from the center. And I also have the frames that are at the center of these patches. So the last thing that I need to do is I need to join the contour of each one of these patches with the circles that I have offset, and I need to join them with a loft. Problem is, though, I do have the surfaces. The surfaces are here, but I don't really have the contour, the edges of these surfaces. Like I said, so the blue lines that I have there. So I need to find that somehow. The way I can do that is by also going to analysis and going to deconstruct brep. If I do that, and if I plug this in here, you can see how this takes any brep, and a surface is a simpler version of a brep if a brep is a brep that only has one surface inside of it. And then it will give me the faces, which are it will give me the edges, and it will give me the vertices of the brep. So if I now plug in here each one of the iso trims, you can see that if I plug in a panel here, you can see that for each one of the 30 surfaces, now what I'm getting is, for example, in the edges, I'm getting a data tree that is 30 branches, and each one of the branches has 4 curves. Each one of these 4 curves is each one of the edges for the isotrim. Now, this is not going to work because I cannot have 4 different curves and then the circle. Because if I do that, and if I love this, it's going to give me something bad. It's going to give me the circle, and it's going to give me this. So it's not going to, not work. Oh, sorry. I plugged into the wrong place. It's not going to give me, you see, it's trying to create a loft around the 4 edges here. So it's not going to work. And also maybe so if I plug this in here, not going to work. So what I need to do is I need to take these 4 curves for each one of the branches, and I need to join them into one continuous curve. That's actually very easy to do because I can go to curves, utilities, and where is join curves. If I do this and I say I want to join all the edges, I don't even need to do any data manipulation because what's nice is that if you remember components work at the list level, which means that this component is going to try to join all the curves that are on the same branch and all the curves that are on the same branch. So how convenient was that this component was giving me edges already in a data tree structure in a way that it made it very easy to join into a closed curve in 3 dimensions. And with this, and with this other tree, I think we are ready to loft, aren't we? So let me loft this, and let me loft this, and then see what the result is here. So am I not getting any result? Oh, yes. So I am getting bad results. So, and what is the problem? Data. Problem is data, because you can see that what's happening is that because these branch names are different than these branch names, they are not combined into the same graph when I plug them together. So for example, if I plug them here and if I plug them here, you can see how they're not combined into the same branch, and therefore there's no loft going from the joint curves to the circles. So what do I need to do now? What I need to do is I need to figure out a way to modify the branches so that they have the same exact structure. So how can I do that? Well, there's two ways to go about this. One would be I could flatten. So for example, what I could do is I could flatten this so that it becomes like one single list, and then I can graph that, and then it becomes a list with two levels. And then I can do the exact same operation here. I'm going to flatten the tree. Here, this becomes a dumb single tree, and then I'm going to graph the tree again, and now it becomes a tree with the same structure. And now I could plug the two things in here. So I could plug this graph and this graph. And then here we have it working. Now, that could be one way to go. It's not very elegant. It takes a lot of manipulation. So what I can do is perhaps do a bit more elegant, which is going to be, I'm going to take this, and I'm going to take this, I'm going to take this tree here, and I can see that they have different structures. So it turns out that there is an operation that I can do on trees that is also called simplify. And simplify is an operation that just removes redundant branches that are not really giving information. So the fact that I have a lot of leading zeros here and a lot of ending zeros here is not really helping at all. So if I simplify this, you can see that the tree just gets into a very clean 0 to 30 kind of branch naming. And if I simplify this one, I will get the same result. So now they both have, again, the same data structure, and I can join them together, and now I get the intended result. Woohoo! And last but not least, I'm going to copy this lofting, the one that had the options. Okay, so I'm going to copy the loft options here. I'm going to remove this, and I'm going to make sure that the seams are adjusted, and now I don't have that problem anymore. All right, and let's bake this and make it a little cool, right? So I'm going to bake this. I'm going to do some rendering here. Yoo-hoo! This looks kind of nice. So, ta-da! Now we have the surface that has this like ocular kind of openings, and or like this egg box kind of thing to them, and it could be the roof of a building, or it could be many things. I don't know. Ooh, that was a lot. All right, so I think with this, I'm a little done. I'm also pretty done for today. I've recorded a lot of tutorials today. So thank you very much. I hope this exercise was useful for learning data manipulation, for learning more properties of surfaces in 2 dimensions, 2-dimensional domains, reparameterization, domains, parameters, etc., etc. And with this, I'm going to call it a day. I'm going to go take some rest. And but I will see you on the next video on this series, which at this point I'm not sure what it's going to be. We're going back to lectures, or we're going to do an exercise. I don't know. just look on the playlist and see what we decided to do next. If this was helpful, if you want to show some gratitude, maybe you want to consider liking the video, subscribing to the channel, and even turning on notifications to see when we go live or when we publish new videos and new content. In the meantime, thank you very much, and hopefully see you on the next videos on this series. Oh my God. Oh, I'm exhausted. How was this? Did you enjoy it? Was it cool? Was it interesting? My batteries are dying. Woohoo! Rolando. Okay, so I think that's it for today. I cannot, I cannot speak anymore. So thank you very much, everyone. Thank you for being here. We will be back live again next week. I want to continue doing this series. I think I may have a couple more days left to wrap everything up, and I really want to make that happen. So we're going to keep streaming next week, and we will probably keep doing this over the weekdays. So thank you very much. Thank you for being here. Oh, thank you for being there. I appreciate the love. Thanks to you, Rolando, for being there. And I appreciate the love, and see you in the next video. See you on the next live stream. Have a nice weekend. Enjoy, go outside, or do whatever you need to do to stay safe, to stay healthy, and to stay happy. Thanks a lot. Bye-bye.